Hello everybody, this is Dr. Christopher White and today we are going to be doing streams and flooding. Alright, let's get going. So what are the goals of this unit? Well, the goals are we're going to describe the general features of stream systems and how they evolve over time. We're going to explain how streams erode, transport and deposit material. We're going to explain how and why stream profiles and other characteristics vary downstream. And we're going to describe the general characteristics of floods and what causes them. Okay, so the vast majority of sediment that's moved on planet Earth is moved by water. And when it comes to moving sediment onto the continents, that means it's going to be moved by rivers. So running water is the most important geological agent when it comes to eroding, transporting and depositing sediment. Nearly every landscape on Earth will show the results of stream erosion or deposition to some degree. So obviously this is a diagram of the hydrologic cycle, and this is a diagram that I would like you guys to know because it might turn up in a test at some point, so be aware. So the hydrologic cycle is something I'm sure you came across in high school, so there's a good chance you're familiar with it already. So obviously the hydrologic cycle starts with the sun warming the oceans, or well, any body of water in fact, producing evaporation. That obviously puts water vapor into the atmosphere. That water vapor will of course condense to form clouds when it gets cool enough. Obviously the clouds will then be moved around in the atmosphere, by air currents in the air. Additional water will be added to the clouds through the process of transpiration. That's when essentially water comes off plants. More evaporation from bodies of water like lakes and rivers, and so obviously that's eventually going to make your cloud grow larger. Now what's going to happen is your cloud is going to cool down at some point. Now that cooling down could just be due to moving into a colder air current, or it could be due to an increase in elevation, because of course as your cloud gets higher in the atmosphere to move over something like a mountain, obviously the air is going to start getting colder. And so that's why most mountain ranges are quite wet environments, because as air hits them it has to try and go over the mountain range. And of course, as the air tries to go over the mountain range, the air gets cooler and cooler and cooler, and that obviously encourages the water vapor to leave the clouds in the form of things like precipitation and snow. So a lot of precipitation will fall in areas where we have high terrain. Now, of course, we in the Houston area are well aware this isn't always the case. We get a lot of precipitation caused by high pressure systems meeting low pressure systems. So, don't just think that rain only happens in high terrain areas. But high terrain areas are a location where significant amounts of rain are deposited. And it just so happens that high terrain areas are also areas where we have lots and lots of rock exposed, which can be eroded by that rain. So, just a happy coincidence there. Anyway, so we'll have evaporation, condensation. The water droplets in the atmosphere will eventually become so large that they will become too heavy to be supported by the air. They will leave the air in the form of precipitation. That precipitation will of course hit the ground. And when it hits the ground, there's one of two things that can happen to that precipitation. Well, it can either move across the surface, so it'll move across the surface in the form of rivers, or it can infiltrate down underground and it will move underground in the form of groundwater. So, as I said, please be aware of this diagram. Please make sure you know this diagram, because there's a very good chance it is going to turn up in tests and in other conversations later on. Okay, so what's a stream? So a stream is a body of running water which is confined to a channel, and it runs downhill under the influence of gravity. And the water itself is provided by precipitation, snowmelt or springs. So the River Thames, which is the largest river in the United Kingdom, actually starts at a spring. So the stream will carry water through a single channel or through a number of interconnected channels. So if you remember, when we're talking about environments of deposition, we discussed that there are actually two main types of rivers. Meandering rivers, they have a single channel, and braided rivers, they have multiple channels all running parallel to each other. So the channels will vary in size. We can have small streams several meters wide to major rivers that are kilometers across. If you've ever seen the Mississippi River, you will know that just how big rivers can get. So A river will drain a very specific area of the Earth's surface, and it will join other smaller rivers to form what is referred to as a drainage network. So typically what will happen is you'll have an area of the Earth's surface, and in that area of the Earth's surface you'll have several small rivers. And normally what will happen is over time those small rivers will coalesce to form one large river. And so it will give a pattern something like a tree. So where do rivers get their sources? Where do rivers get their water from? Well, it's pretty obvious that the water can come into a river in a few ways. It can either come directly from the atmosphere. So when you have a rainstorm, a raindrop can fall straight from the atmosphere into a river. Another option is that the water can move across the land. And the final option is that the water can enter the river via groundwater. So those are our three main options. So when it comes to rivers, we classify them in just a couple of ways. I'm sorry, I'm just going to have to reach over here for a second. Sorry about the noise, I do apologise. So the first type of river is referred to as a gaining stream, also referred to as a effluent stream, and this kind of river receives water from the groundwater. Now this means it is a perennial river. It will flow all year because there is a constant supply of water coming into the river via the groundwater. Then we have what's referred to as a losing or influent stream, and these are streams that sit above the water table. So the water table essentially is this line here. Okay, this is the water table. This is where the top of the groundwater starts. If you have a river that's sitting up here above the water table, well, it can't get any water from the groundwater. So the only way that these rivers can get water is by water falling directly in from the atmosphere or by water flowing over the ground. So as I said, these are referred to as losing or influent streams. They lie above the water table, and what will happen is they are not constant. They do not flow all year round. So they're referred to as ephemeral streams. So we have perennial, all year round, ephemeral, not all year round. Now, around any river, we are going to have a floodplain. So a floodplain is a flat area, well, a flat floor composed of sediment which is deposited by the river. All right. So let's have a look at these two examples here. So this is the meeting of the Missouri and Mississippi rivers. In this case, you can see this is 1991, where there's no flooding, and this is 1993. We can quite clearly see there is flooding. So one of the things that floodplains, especially around meandering streams, have is very, very good quality soil. So if you look at this image here, you'll see there's lots and lots of farmland along the floodplain or on the floodplains, because the floodplains here are a mixture of clay and silt deposited by the river, a little bit of sand, and also a lot of organic material that's deposited in the river as well. And so all of this material essentially helps to regenerate the soil every time the river floods. So when it comes down to it, rivers flooding is actually a relatively positive thing. It's just really annoying if you happen to have built your house in an area which floods. So, there's pros and cons to rivers flooding. But what we can see here is we can see we have a ridge coming along here. So this area is high ground. So when the river floods, obviously it did not flood this area back here because it's high ground. What we can see though is these areas, this area here is also high ground. We can see that didn't flood. But we can see these areas here, which you can see are quite flat. Well, those are the floodplain areas, and you can see those have been flooded. And in this image here, what you can see is we have green, which is the vegetation, and we have red, which is the exposed sediment. So this is the sediment that's being deposited by the river as it floods. And so what we can see here is that the river water would actually have covered over all of these areas that were red. So the flood would actually have been more expansive than is shown in this image here. But anyway, floods, in one way good, in other ways bad. Okay, so let's look at the major drainage basins of continental North America. So as you can see, we have 5 main drainage basins. We have the Atlantic Ocean drainage basin, and the rivers in this area will drain, of course, into the Atlantic. Shock horror. we have the Gulf of Mexico drainage basins. The rivers in this area will of course drain into the Gulf of Mexico. Arctic Ocean drainage basin, the rivers drain into the Arctic Ocean. Pacific Ocean drainage basin, well, they're going to drain into the Pacific Ocean. And then we have what's referred to as the interior drainage basin. This is an area of subdued topography, so the crust actually dips down, and so the water naturally flows into that depression. And so rivers that form in this area can't make it to the Pacific because they naturally flow towards the center of this drainage basin. So these are the 5 major main drainage basins of continental North America. Now, here we have a very important term, tributary. So a river will have one main channel, and into that main channel, smaller rivers will come. They'll attach themselves to the side of it. Now, these smaller rivers which contribute water and sediment to the main channel are referred to as tributaries. So as we can see here, so let's just say this is the main channel coming along here. Here it comes. That's the main channel there. Well, this would be considered a tributary. This would be considered a tributary, and this would be considered a tributary, because they're essentially coming into the main channel and contributing water and sediment to that main channel. So these areas of the Earth's surface which is drained by a river and its tributaries are referred to as its drainage basin. So if we look here, here's the drainage basin for the Mississippi River. All right, so the Mississippi River, we go back to the previous slide. So here's the Mississippi here. Okay, and then we have the Missouri over here and the Ohio over here. So Missouri here, Ohio here, and they are tributaries. Missouri, Ohio, they are tributaries to the Mississippi here. All right. Oh, just a quick aside while I suddenly remember. If you notice the basins that we have here, the 5 basins, are actually separated by areas of high ground. So just take note here. The Atlantic Ocean basin, well, you have a ridge of high ground here, which we refer to as the Appalachians. So the Appalachians are separating the Gulf of Mexico basin on the western side from the Atlantic Ocean basin on the eastern side. Now, in the case of the Arctic Ocean basin, what's happening there is that's due to the effects of glaciation. So this area here essentially is depressed because of the weight of the ice from the previous ice age. So this area here is actually a topographic low. So water that's falling into this area essentially flows towards the Arctic Ocean. There's also a whole line of glacial deposits which essentially form a crudish wall along here. These were left by the ice sheet at the end of the last ice age, and so that also helps to form a barrier between the Gulf of Mexico basin down here and the Atlantic Ocean basin over here. Obviously we have the Pacific Ocean basin here. Well, the margin of that of course is the eastern margin of the Rockies. And then of course we have the interior drainage basin over here. This area is of course an area that's separated by a whole range of higher ground areas essentially around it. So essentially this is the low ground in the middle, and we have a ring of high ground to the sides, and so obviously the water comes off the high ground into the interior drainage basin. So there are barriers that essentially help to mark out the boundaries of drainage basins. So a drainage basin is separated by a ridge of high ground that divides one drainage basin from another, in most cases. So if we look at this diagram here, we have one drainage basin here marked in blue, one drainage basin marked here in red, and we have the ridge line coming down here separating the two. And so if any water falls on this side of the ridge, it goes into this river, falls on this side of the ridge, it goes into this river. So the boundary between two drainage basins I've heard referred to by several terms. It's been referred to as the watershed, the drainage divide, or the ridge line. So these 3 terms essentially mean the same thing, and they're interchangeable. So in the case of the continental North America, we have what's referred to as the continental divide, and that separates the streams of the Pacific from the streams of the Gulf of Mexico. And you can see the continental divide is essentially the Rockies, the eastern boundary of the Rockies. Okay, so what about drainage patterns? Well, as discussed, rivers and tributaries will form distinct patterns, and there are 4 main patterns which we see. The first type is referred to as dendritic, which means it looks like a tree. And this is an example of a dendritic pattern up here. And this is a very simplified version of it. You can see you have one main channel to which you have lots and lots of tributaries joining. And it gives an appearance a lot like a tree. Now that's a very, very common pattern. And that's a pattern I'm sure you might remember having seen in high school geography. Then we have a radial pattern. So a radial pattern is produced when streams diverge outwards like spokes of a wheel, and this is very, very commonly seen where you have a single bit of high ground. So something like a volcano or or a mountain all by itself. And so what will happen is the water will hit somewhere on the mountain, and obviously it will then flow down the slope, and so it will flow away from the high point in the mountain in all directions depending on wherever the rain is falling. And so what you get is you get several rivers all coming away from a central point, and your central point is obviously your volcano, your high ground. Then we have what's referred to as a rectangular pattern. So as you can quite clearly see, if you just look at the picture here, you'll see the rivers and the tributaries are all joining together at approximately 90 degrees. And that's because the tributaries and the rivers are exploiting joints, so cracks, in the rock. And so in a lot of cases when you have a rock and it's allowed to expand, so imagine if you're a rock and you've been buried 20 kilometers underground, you're under huge amounts of pressure. And then as you come towards the surface, so as the rock above you gets eroded away, so the 20 kilometers of rock above you get eroded away, and all of a sudden you find yourself at the Earth's surface, the pressure is really, really low while the rock goes and it expands. And as the rock expands, because the rock is a brittle substance, it cracks. And it just so happens that a lot of the time when the rock cracks, those cracks will form at 90-degree angles to each other. So it's not uncommon to find joint sets where the joints intersect at 90 degrees. So if you have an environment like that where you have these joints at 90 degrees to each other, it's not uncommon for, number one, the water to exploit the joints, because they're a very easy path for the water to move along. And so the water naturally does that. Remember, water will always take the path of least resistance. And so the water just, comes along the joints. And so obviously over time, it will exploit the joints. It will make the joints wider. And so obviously, you'll end up forming proper rivers along those joints. But the joints themselves will essentially be guiding the path that the river takes. So the fact you have these rivers and these tributaries all meeting at 90 degrees is a reflection of the fact that the rock is full of these joints and the joints are meeting at 90 degrees. So rectangular pattern tends to occur in areas like that. And you can find this kind of pattern occurring in places like Ireland especially. So there are some very nice examples of this type of river occurring in Ireland. The final type of river is what's referred to as the trellis pattern. So the trellis pattern looks like this. And the trellis pattern occurs when you have lots and lots of linear valleys, so long valleys, all running parallel to each other. And obviously in between these valleys, you're going to have a ridge of high ground. This is the kind of type of river pattern we see a lot in the Appalachian Mountains. So as you can see here in this diagram, we have a river valley here, a river valley here, and a river valley here. And you can see at the base of the river valley, you have one main river flowing from top to bottom in the image. See it there, and you can see it there. But you have lots and lots of very, very small rivers coming off the ridges either side, the high ground either side, joining up with this one main channel. So what you end up with in a trellis pattern is you have one big river and you have lots of very, very short rivers joining it from the sides. And so you end up with a pattern that looks something like this. And so that's a trellis pattern. So these are the four main types of drainage pattern that a river will show. So in terms of
rivers themselves, well, why are geologists really interested in rivers? Well, obviously there's the fact that rivers obviously form essentially transport and deposit large quantities of sediment. But there's also the fact that when you think about it, the paths that are being taken by rivers are directly reflected by geology. So a river will tend to take the path of least resistance, and the path of least resistance in a lot of times will be something like a geologically weak layer of rock, something the water can erode very, very quickly, creating a natural depression along which the water will move. It could be something like a fault. A fault on the surface of the earth can essentially produce a noticeable crack, a noticeable weakness on the surface of the earth. Water will naturally move along that because it's the path of least resistance. As you've already discussed, if the rocks have joints in them, then once again the water will exploit those joints because they are the path of least resistance. So geology has a very, very strong influence on the position of rivers and also the type of drainage pattern that you see. So the drainage pattern we see reflects rock types, the geometry of folds and faults and joints in the rock, and other structural features. So geology controls rivers, and rivers of course are important to geology because they transport the sediment that of course leads to the formation of lots of clastic sedimentary rocks. So one of the things that you might know about rivers, and chances are you've seen this but you may not have thought about it, is that rivers obviously change in their energy. So if you think of the Mississippi River, you look at it, it's quite a, it's big, granted, but it's quite a gentle body of water, isn't it? It just flows along in a kind of lazy kind of fashion. But then I'm pretty certain most of us will have seen pictures of people white water rafting. And obviously you'll know from that situation, the rivers are quite violent. Their water's moving very, very quickly with lots and lots of energy. And so the obvious question is why is that? Well, remember that water is dropping downhill under gravity. So the steeper the gradient, the faster the water is dropping. So if we have a look at this diagram here, okay, this diagram is discussing gradient. So let's just have a look at this gradient here. Okay, as we come 1 kilometer this way, we drop down 15 meters. So that means the water for every 1 kilometer laterally is dropping down 15 meters vertically. That's quite a big drop. So obviously that means the water is moving quite fast. As we come down here, for every 1 kilometer laterally, it's only dropping 8 meters vertically. And down here, for every 1 kilometer laterally, it's only dropping 4 meters vertically. So you can see is that as you come down a river profile, the gradient gets lower, and so the rate at which the river drops every 1 kilometer laterally or so becomes smaller, and so essentially the river begins to lose velocity. So you'll find the steeper gradient towards where the river's starting, and you'll find the lower gradients towards where the river is coming to an end. Now, how do we calculate gradient? Well, gradient is calculated by taking the vertical change and dividing by the horizontal change. Okay, so in this case, of course, it would be 15 meters divided by 1,000 meters, because remember, you've got to keep those units the same. All right, so don't get caught out by that. Or essentially, this change would be 15 meters by 1,000 meters, and that's going to give us our gradient. So as discussed, the steeper the gradient, the stream will drop quickly, essentially over a given distance, meaning the water drops faster under gravity, so it has more velocity. The gradient decreases downstream, and gradients will often be described in meters per kilometer or foot per mile. Sometimes they'll be described in degrees or percentages. So, if you've ever driven anywhere that has topography, if you've ever gone west of Houston towards hill country, you'll know that when you start having signs telling you about the gradient, they'll typically be shown to you in things like, percentages. Okay, so the fact that we have these chains of change in gradients affects the water's velocity. Okay, now that means as we move from the river's head to essentially its mouth, we will see that the type of river we get will change, because the velocity at which the water is moving affects the type of river we see. So in these very, very high mountainous areas, the water is dropping very, very quickly, so the river has lots of velocity, it has lots of energy. And so what does the river do? Well, what the river does is the river just essentially punches its way downstream. It just straight lines it. And so you can see down here in the bottom left, what do we have? Well, here we have the classic mountain river. It's got a V-shaped valley, and the river itself is following a pretty straight pattern. And so it also is a single channel, by the way. So you get all the water focused along one relatively straight river channel, and that river sits within a V-shaped valley. And of course, as you might be able to tell, that is called a straight river. Shock horror. Now, as the gradient begins to drop, we lose a little bit of velocity. The water is still moving quite quickly though. And so at that point we transition from straight rivers to braided rivers. So water in braided rivers is moving quite fast, but there's lots and lots of very, very loose sediment, and so because the water is moving quite fast, it can take whatever path it wants because it has lots of energy. So this river can cut through this loose sediment really, really easily. So one bit of the river decides to go this way, one bit of the river decides to go this way, and one bit of the river decides to go this way. So you have multiple channels all running parallel to each other, and they all crisscross on each other. Finally, as we come down here towards the mouth of the river, the gradient's going to get quite shallow, and at this point the water is going to be dropping quite slowly. So the river is essentially losing velocity, it's losing energy. And so at this point, what the river decides to do is it takes the easiest path, which is all the water that was in multiple channels in a braided river system. It focuses all that water together into just one channel. And that river will then take the path of least resistance, essentially towards the coast or sea or lake, wherever the water is going to eventually finish. Okay, now what this means is essentially in these very, very high up mountainous areas, we have water with lots and lots of power. So we have erosion taking place. Down here towards the lower portions of the profile, we tend to have a river that's moving more slowly, which will more commonly flood. And so in this area here, we tend to have a lot more deposition taking place. What this means is over time, you'll end up producing what's referred to as, the concave upward profile. And this is what every river is trying to achieve. Every river is desperate to achieve this concave upward profile because it is the most efficient profile for a river to have. And this is the concave upward profile here, marked out by this yellow dashed line. And so what you can see is over time, the river will naturally erode away all of this material above the profile. And down here, for instance, we may have material being deposited, essentially to bring up the profile. So all of this material needs to be removed. And in some cases, you may require deposition to fill in low points. And eventually you'll have this concave upward profile, and this will be the perfect profile for your river. It will be the most energy efficient profile for your river. So all rivers are trying to achieve this profile. Okay, so this is the last slide we're going to look at, then we're going to stop the video here. So let's look at the final thing, is the factors that will actually influence the profiles of our rivers. So as we've discussed, geology has a very, very important part to play when it comes to rivers, how they, essentially the paths they take, but also it's going to affect the profile. Now, if you have a profile where you have a sequence of soft rocks, your river will be able to erode efficiently, and so it will end up producing a nice smooth profile very, very quickly. In contrast, if we have a situation like over here, where we have certain layers of rock which are quite hard, in this case the hard layers of rock are going to be these tan-coloured layers here and here, we can see that where the rock is soft, it produces these relatively flat profiles, but where the rock is hard, it tends to produce these quite steep drops. And that's going to produce a profile that has cliffs and waterfalls. Now over time, all of this will eventually be eroded away to produce a nice smooth profile like this, but it takes a lot longer because of the hard rocks. And so if you want to produce a nice smooth profile, you can produce it much faster in an environment where you have soft rocks rather than hard rocks. Okay, what else is going to affect our profile? Well, tectonics, pushing, raising and dropping of the crust by tectonic processes. So what happens? Well, if we start pushing the crust up, what does our river end up doing? Well, if this was our original position here, the top of this grey block, and the crust gets pushed up by this extra amount, well, what's happening? Well, all of a sudden the water up here is finding itself in a much more topographically high location, so therefore it's dropping faster under gravity, so the water starts to move faster, and so the water has more erosive power. And so in areas where the water starts to get pushed upwards, where the rock starts to get pushed upwards, what you'll see is the river starts to move more quickly and it starts to cut down very, very fast because it has all of this extra erosional power. And this is exactly what we see in the Grand Canyon. The only reason the Grand Canyon exists is because about 40 million years ago, that entire area started to get pushed up. And so what did the Colorado River find it? And so the Colorado River suddenly found itself in a situation where all of a sudden the gradient was starting to get steeper. And so the Colorado River started to have more energy, more velocity, and so it started to erode down very, very quickly, producing the Grand Canyon. So where we have tectonic uplift, it's going to produce rapid erosion and canyons. Where we have subsidence, well, what we're going to see is we're going to see the profile will typically be more gentle, and the subsidence will often lead to the deposition of very, very large amounts of sediment towards the mouth of the river. Once again, changing the profile. Sea level. Sea level can also affect the profile that we see. So a sea level, when it goes up or down, changes the base level. So what's the base level? Well, if we just come back to this diagram here, this concave pattern that we see here represents the base level. That's the lowest point to which a river can erode. Now, think about it. If this point here is the end of the base level, then the sea is going to be right here. If the sea drops to a level down here, then all of a sudden the base level is going to be down here, isn't it? And so the concave profile is going to become more like that. If the sea comes up, so the ocean is now here, obviously the ocean is going to come onto the land, it's going to be about here. Well, in that case, obviously what's going to happen is you'll need to have deposition of sediment here to essentially fill in the missing rock. So that's what you have to bear in mind. As the sea level goes up and down, it changes this base level. So if the sea drops, it produces a steeper gradient and you get a river that cuts down very, very quickly. If the sea level rises, it causes erosion to move towards the head of the river, and it causes deposition towards the mouth of the river. So once again, we're going to see a change in our river profile. Okay, then of course there's climate. Climate's a pretty obvious one. If you have a steady, continuous climate, it's going to allow your river to achieve its perfect profile faster. So if you have a situation where you get constant rain, then your river is constantly flowing at a constant rate, constantly eroding, and your river will achieve its profile quite quickly. If, however, you have a situation where the river only gets replenished by rainwater once every 10 years or so, well, it's only once every 10 years that your river will actually be flowing and eroding. And so in that situation, obviously, it's going to take a lot longer for your river to actually achieve its preferred profile. The final variable is, of course, stability of conditions, and that ties back into the climate. So if you have stable conditions for long periods of time, it lets the river achieve equilibrium faster. Okay, so stable conditions means that your river has a lot of water. But I should also point out that rivers in area that can have very, very high rates of rainfall will also achieve their profile a lot faster than areas which have lower rates of rainfall. Okay, so we're going to stop there for now. So this is the end of video 1, and come back for video 2 once you've stood up, had a walk around, got yourself a drink of water, cup of tea, cup of coffee, and relax for a few minutes. All right.